From nuclear bombs to giant mirrors, over the decades, humanity has dreamed up some of the wildest ideas to make Mars not just the next great frontier, but a second home for humankind. The question on everyone's mind is, could we actually terraform Mars by the year 2100? To answer that, we have to take a deep dive into our current understanding of Mars, the technological hurdles, and the radical, sometimes even outlandish, concepts scientists have proposed to transform the red planet. Let's begin with Mars as it is today. Mars is a cold, dry desert world with a whisper-thin atmosphere, mostly carbon dioxide, and surface temperatures that can plunge to minus 125 degrees Celsius at night. Water exists, but mostly locked away as ice at the poles or as vapor in the thin air. Radiation from the sun bombards the surface, unfiltered by a protective magnetic field or thick atmosphere like Earth's. For life as we know it, Mars is a hostile place, but the allure of turning Mars into a blue-green world has captivated our imagination for generations. The term terraforming itself means shaping a planet to be more Earth-like, to support human life without the need for bulky spacesuits or pressurized habitats. The dream is bold: to create breathable air, flowing water, and a climate warm enough for plants to grow under an alien sun. The first step, most scientists agree, would be to warm up Mars. The average temperature on Mars is about minus 60 degrees Celsius, far too cold for liquid water to exist on the surface. If we could somehow raise the planetary thermostat, perhaps we could coax the polar ice caps to melt, releasing water and carbon dioxide into the atmosphere. But how could we achieve such a monumental task? One of the most famous and controversial ideas comes from none other than Elon Musk, who proposed detonating nuclear bombs over Mars's poles. The theory is that the energy from the explosions would vaporize the ice, releasing greenhouse gases into the atmosphere, which would then trap heat and kickstart a runaway warming effect. It sounds like science fiction, and in many ways it is. The logistics alone are staggering. The number of bombs required, the unknown effects on Martian geology, and the ethical questions of detonating nuclear devices on another planet are just the start. But nuclear bombs aren't the only wildcard on the table. Another concept involves building giant orbital mirrors, massive sheets of reflective material, perhaps kilometers across, that would focus sunlight onto the Martian surface. By concentrating sunlight, these mirrors could gradually heat up targeted regions, again releasing stored gases and warming the planet. While the idea sidesteps the radioactive fallout of nuclear detonations, it presents its own engineering nightmares. Constructing, transporting, and precisely positioning such colossal structures in orbit would require technologies we're only beginning to imagine. Other proposals are more subtle, but no less ambitious. Some scientists suggest releasing potent greenhouse gases, like perfluorocarbons, into the Martian atmosphere. These synthetic gases, far more effective at trapping heat than carbon dioxide, could be manufactured using Martian resources and released over decades or centuries to slowly build up a warming blanket. The catch? We'd need a massive industrial infrastructure on Mars, and producing enough gas to make a difference could take centuries. Let's say, through one or more of these methods, we managed to warm Mars significantly. The next challenge is thickening the atmosphere. A denser atmosphere would not only help trap heat, but also provide some protection from cosmic and solar radiation. Here, Mars deals us a tough hand. Its gravity is only about 38% that of Earth's, making it hard to retain an atmosphere over geologic time. And unlike Earth, Mars lacks a global magnetic field to shield its air from being stripped away by solar wind. Recent studies suggest that even if we melted all the ice caps and released all the trapped gases in the Martian soil, we'd still fall short of Earth-like atmospheric pressure, perhaps only reaching 1 to 2% of what we enjoy on our home planet. To get any further, we'd need to import gases from elsewhere, or find ways to prevent ongoing atmospheric loss. Creating an artificial magnetic field has been proposed, perhaps by deploying a massive magnetic shield at the Mars-Sun L1 Lagrange point, deflecting the solar wind. Again, the scale of such a project boggles the mind. Suppose, though, that we overcome these obstacles and create a thicker, warmer atmosphere. The next hurdle is breathable air. Mars' atmosphere is mostly carbon dioxide, with only trace amounts of oxygen. To make the air safe for humans, we'd need to convert enormous amounts of CO2 into oxygen. This could be done through ecopoiesis, introducing hardy microbes or genetically engineered plants to the Martian surface, gradually transforming the air through photosynthesis, as cyanobacteria did on early Earth. But this is no overnight fix. Even with the best bioengineering, it could take thousands of years to build up enough oxygen for humans to breathe. And there are questions about whether Earth life could survive on Mars, even after warming. The planet's soil is laced with perchlorates, toxic chemicals that would hinder most life forms. Creating fertile ground for plants might mean terraforming the soil as well as the air. Water is another major concern. Melting the ice caps would release some water, but not nearly enough to create oceans or even lakes on Earth's scale. We'd need to find ways to tap into underground aquifers or import water from comets and asteroids. Technologies for mining and redirecting icy bodies are in their infancy, and the energy costs would be immense. As daunting as all this sounds, it's worth remembering that terraforming is not an all-or-nothing game. Partial terraforming could make Mars more hospitable, raising temperatures enough to allow plants to grow in greenhouses, or thickening the atmosphere just enough to reduce radiation exposure. Human settlements could be pressurized domes or underground habitats, slowly expanding as the environment improves. But could this all happen by 2100? Let's look at the timeline. As of today, no humans have set foot on Mars. The first crewed missions are tentatively targeted for the late 2020s or early 2030s, and establishing a permanent base could take decades more. Building the industrial infrastructure needed to manufacture greenhouse gases, construct orbital mirrors, or deploy magnetic shields would likely be the work of generations. Most experts agree that fully terraforming Mars by 2100 is wildly optimistic, if not outright impossible, given our current technology. Even with unlimited resources and global cooperation, the physical and engineering challenges are enormous. The timeframes for warming the planet, thickening the atmosphere, and generating enough oxygen all stretch into centuries, not decades. But that doesn't mean we shouldn't try. The process of terraforming, even if it takes thousands of years, would begin with small steps: building habitats, experimenting with closed-loop life support, testing crops in Martian soil, and slowly learning how to manipulate the planet's environment. Along the way, we develop new technologies, make discoveries about Mars and about ourselves, and perhaps inspire a new era of human exploration. There are also ethical questions to consider. Mars is a pristine world, untouched by life as we know it. Do we have the right to change it? What if we discover native Martian microbes clinging to survival underground? Should we preserve Mars as it is, or is it our destiny to spread life to the stars? These are questions scientists, philosophers, and policymakers will have to grapple with as we move forward. Some argue that the resources and energy required for terraforming would be better spent protecting and repairing Earth. After all, we already have a blue planet. Why not fix what we have before remaking another? Others counter that learning to terraform Mars could teach us how to reverse climate change on Earth, or help us survive if disaster strikes our homeworld. And there's the sheer audacity of the dream. Humanity has always reached for the impossible, building pyramids, crossing oceans, landing on the moon. Terraforming Mars would be the ultimate test of our ingenuity, perseverance, and vision. In the early decades of Mars exploration, we'll likely see a focus on survival, building habitats, growing food, recycling air and water. As our foothold grows, we'll experiment with para-terraforming, creating controlled Earth-like environments under domes or in underground caverns. These mini-Earths could serve as testbeds for larger-scale interventions. Gradually, as technology advances, we might attempt regional terraforming, warming specific areas, introducing hardy plants, loosening the soil. The lessons learned could inform future generations, who might one day look up and see clouds drifting across a blue Martian sky. But by 2100, Mars will almost certainly remain a frontier. Harsh, challenging, and awe-inspiring. The first steps toward terraforming may be underway, but the dream of a fully Earth-like Mars will still lie in the distant future. Yet in every great achievement, it is the first steps that matter most. The seeds of terraforming will be planted by the engineers who build the first habitats, the biologists who coax the first plants to grow in Martian soil, and the visionaries who dare to imagine a world transformed. So, could we terraform Mars by 2100? Realistically, no. But could we begin the process, laying the foundation for future generations to continue the work? Absolutely. The journey will be long, filled with setbacks and triumphs. But the greatest adventure in the history of our species may be only just beginning. From nuclear bombs to giant mirrors, and ideas not yet dreamed of, the story of terraforming Mars is a testament to human creativity, ambition, and the unquenchable desire to reach for the stars.